Hello, hi, my name is Kanak Saha. I am a faculty member at the Inter-University Center for Astronomy and Astrophysics, Pune, India. Today, I'm going to talk to you about galaxies, how galaxies are formed, their structure, and how galaxies evolved since their birthplace. This talk will also be centered around the Milky Way galaxy, our home galaxy. Milky Way is the only galaxy where we can do star count analysis in unprecedented detail, thanks to the Gaia satellite. Throughout this talk, I'll also try to connect various galaxy properties with what we know from the Milky Way studies. Milky Way is like a reference galaxy if you want to understand the galaxy formation, galaxy evolution. Hence, the title of this talk today is the Milky Way as a cosmic classroom. This is a artist impression of the Milky Way galaxy. At this point, where lies our solar neighborhood, which is around 8.5 kiloparsec from the center of the galaxy. This is the center of the galaxy. And the sun, with all its planets, goes around the center of the galaxy with a speed of nearly 220 kilometers per second. The galaxies are made up of billions of stars. For example, Milky Way have about 10 billion stars. Apart from the stars, there are interstellar medium, the medium between the stars. This is composed of atomic hydrogen, molecular hydrogen, ionized gas, and various phases of the interstellar medium. Apart from stars and the ISM, the galaxies are sort of immersed in the invisible dark matter halo. This is another image of a galaxy, which is a barred spiral galaxy, like our Milky Way galaxy. And this galaxy hosts a very, very massive supermassive black hole, rather. It's about 174 million solar mass black hole compared to the Milky Way galaxy, which hosts about 4.2 million solar mass black hole. If we look at the galaxy or Milky Way in the Hubble classification scheme, the Milky Way is close to SBC type. S stands for spiral, B stands for the bar, which is like elongated structure. See the elongated structure like this. And C stands for how open or tightly the closed the spiral arms are. In C, the spiral arms are open, and in A, the spiral arms are tightly wound. So the Milky Way, in a simple sentence, is a barred spiral galaxy. Apart from the spiral galaxies, which are the Hubble-Tinning diagram, occupies the Hubble-Tinning diagram, there are galaxies which are the elliptical type, which is like E0 here. 0 means it's like a more like a spherical, and 3, 4, 5, 6 makes is very elongated as it be projected in the sky. Apart from the elliptical and spirals, there are galaxies which are lenticular galaxy or the S0 galaxy, which have no spiral arms. And apart from the elliptical, the lenticular, and the spiral galaxies, these are the irregular galaxies which have no obvious shape and size to be described in simple terms. So they are the irregular galaxies. This is a small mosaic of galaxies in the local universe. This is to show you the morphological diversity that we know from the local universe. This is an elliptical galaxy, and this is where is a, as you're very familiar, the barred spiral galaxy, and this is a spiral galaxy without any bar. And then you can see there are rings of stars, which is in the galaxy. This is a ring. This is another kind of ring. This is a cartwheel type of galaxy, and this is a Hawke's ring. The ring, which is apparently like, no, we don't see any like disc type of material, but it's like very ring. And then the galaxies we are like very irregular. Like some of the galaxies like very faint and diffuse, and also galaxies we are like very like strange new type of galaxies. These are all the green pea kind of galaxies. Galaxies, when look at in the age on, they look like this or like this. Means that we can see the how thin or thick the disk is of the Milky Way. And these are known as super thin galaxy. Overall, if you look at even the galaxies from this like green pea to the elliptical, the big elliptical galaxy, they have a huge dynamical range in the stellar mass, right? Going all the way up from 10 to the power 13 times the mass of Sun to 10 to the power 5 times the mass of Sun. This morphological diversity with the dynamic range provides a unique or like very strong challenge to the galaxy formation models. Let us look at the Milky Way stellar disk. Milky Way stellar disk is non-symmetric. It means axially symmetric because it has a bar and also a spiral arm. Now, if you look at, for example, if you take any radius, let's say r, which is from the center, and go in azimuth, and as you go in azimuth, you will encounter a spiral arm where the density will be higher, and then like the density will be lower, and then go around again, the density will be higher, and like that. Which means that the surface density distribution will depend on the radial coordinate from the center and also the polar coordinate from the phi angle, azimuthal angle. If we azimuthally average all this surface density, it follows the radial density distribution follows an exponential profile, and on a log normal plot, it becomes a straight line. The stellar disk of most spiral galaxies follow an exponential profile along the radial direction, which is like universally true. Milky Way hosts a boxy bulge as well. Perhaps there is a hidden small classical bulge of larger origin, and it hosts a supermassive black hole of 4.2 solar mass, as I said earlier. In the vertical direction, this is an edge-on view of the Milky Way taken from the Kobe satellite, 1995, and reconstructed image of the Milky Way. Now you can see that the Milky Way stellar disk is quite thin, and if you look at the density distribution and along the vertical directions, one can actually measure this density distribution. However, it's a very simple thing. So if one can actually analytically find out what the density distribution is expected. If there is only stars and the stars follow an isothermal distribution along the z direction like this, where E is the energy, the vertical energy of the star, the kinetic energy and the potential energy, and if we use the Poisson equation under very thin disk approximation, which is this, then one can solve for the density distribution, and it comes out to be sec h square density profile, sec h square profile. Z naught is basically the scale height, or it represents how thick the stellar disk is. Okay, and it depends on the vertical velocity dispersion. So it means in the vertical directions how the velocity dispersions, and the square root of 0, 1 over square root of 0 is actually the free fall time scale. Rho naught is the midplane density. Now, if you look at the thin disk in actual galaxies, they may follow like this because it's a very thin. But if you have the enough resolution and the sensitivity, one can actually find that that many spiral galaxies have in the vertical direction and extended the density distribution of stars, which is different from the thin disk profile, and this is the thick disk of the galaxy. And Milky Way has a thick disk. Thick disk stars follow a different density, and they are chemically distinct from the thin disk stars. When you're talking about the vertical distribution, overall, the geometry of the Milky Way disk is quite interesting because the plane of the Milky Way galaxy is warped, and one side is bent up and the another side azimuthally opposite direction. It's a bend in the downward direction. This is basically the classic S-shaped warp, and this is shown in terms this 3D plot, which is the Z on this axis and X and Y on this. And these blue dots or the green are basically the Cepheid variables for which we can actually measure the distance very accurately, and one can map them and trying to trace the warp of the Milky Way, thanks to the Gaia satellite for allowing us to do that. Apart from stars, there are gas in the galaxy. This is what maybe more than 50 years old plot of surface density distribution of gas as a function of radius. This is where the sun is located, and this is the molecular hydrogen distribution, and this is the neutral hydrogen gas distribution, the dashed line. This is the ionized gas. One can see this plot of the neutral hydrogen gas, which is remaining flat around the solar neighborhood, which is actually solar neighborhood. But the new surveys, the one that this plot is made from the Leiden, Argentine, and Bonn survey, one can see that the gas distribution extends much beyond, and it goes all the way up to around 30 kiloparsec. This neutral hydrogen gas is actually observed through a 21 centimeter emission or 1420 megahertz emission, which comes from the spin flip transition of electron in a ground state of hydrogen atom. So if you want to look carefully, like this, what comes out is that the gas extends far beyond the optical boundary of the galaxy. And in Milky Way, it is almost twice the optical radius. The same is true in external galaxies. This is M83 in red. What you see is the 21 centimeter emission of gas, and you can see that this is where the stars like sort of ending, and you see the gas is like much beyond. And the same thing is like true in the NGC 3198. In black, you have the optical image taken from the Palomar, and on white, you see basically the surface density contours of neutral hydrogen gas. So in most galaxies, the extent of the H1 disk is much larger than the optical extent of the galaxy. Well, thanks to the deep photometry, actually, and the recent advances show that even one can actually trace stars, which is far beyond what was known about few years ago. This is what was known about few years ago, but now because of the deep photometry, we are actually seeing the old stars like extending far beyond where the galaxy were supposedly ending, and this can actually lead to a very interesting study that where is the actual boundary of a galaxy actually. So does it mean that the galaxy continue to extend so it's like an improvement in the sensitivity of the telescope and the photometric technique, which allows you to basically recover, find out how far a galaxy extends, and this is a very fascinating study. Now, one can use the fact that the gas extends very far from the stellar disk, so the gas would be moving almost like a ballistic particle. So the gas cloud, one can actually make the measurement of the circular velocity of the neutral hydrogen gas, and when you plot the circular velocity of neutral hydrogen gas, it seems like as a function of radius, and at largest radius they stay almost flat, which means the circular velocity is nearly constant. And this is where you can see this is the plot showing that the surface density or the surface brightness of stars, stellar light, as a function of radius. And you can see this is where sort of the stars end, and beyond which the gas is still remaining flat. And if you get the contribution of the circular velocity from the stars and gas together, it is not able to explain this circular velocity. And this has led to the discovery or that there is dark matter in spiral galaxies, in galaxies in general. And thanks to the pioneering study of famous astronomer Vera Rubin in this context. Now, if you consider that the dark matter is spherically distributed around the baryonic matter distribution in the galaxy, then we can talk about the circular velocity is basically gm over r. Since vc is the circular velocity is constant, then am of r must be proportional to r to keep the vc constant, right? And then one can deduce from there that you can just solve this little integral, and then rho, the density of this invisible matter, must be proportional to 1 over r square. And this is the well-known singular isothermal density profile solution. And since m is proportional to r, m goes to infinity as r goes to infinity, which means that this is also an unphysical solution. And various dark matter profiles are being proposed to explain that circular velocity in spiral galaxies. This is one of the profile called the pseudo-isothermal dark matter halo profile, and it has a core. And this is the NFW profile, Navarro-Frank and White dark matter halo profile, where it has a cusp at the center. The cosmic halos are basically favored in simulations, which means that when cosmological simulations are done, the dark matter halos which collapse, one can actually deduce the density of the dark matter, and it seems they are sort of cuspy. Okay, this cusp and core is not yet resolved. Means that whether the galaxy prefers a cuspy profile or the core profile, or the cusp or core get converted to each other, it's not clear yet. Let's look at the motion of stars and gas in a very simple and sort of simplified way. So one can think about the stars actually move in the galaxy in epicycles. In a simplified picture, one can think of them moving in a circular orbit and with azimuthal frequency omega of r. While it oscillates in the circular orbit, while it rotates in the circular orbit, it also oscillates in the radial direction with epicyclic frequency kappa about the circular orbit, and also in the vertical direction with the frequency nu of r. In general, galactic potential or in galaxies, omega is not equals to kappa, not equals to nu, which means that if a star is starting from A at t is equal to 0, it will go around in an orbit and it will not come back at the same location because omega is not equals to kappa. This leads to the fact that the orbits are actually not closed in galaxies. Okay. However, one can actually do some clever tricks and make the orbit closed, especially if you go in the rotating frame. Now, those bars and spirals that we talked about which are present in the Milky Way, the bar has a pattern speed. So bar rotates with almost like a rigid pattern in a galaxy, and one can go into the rotating frame and suitably adjust the rotating frequency, the rotating pattern frequency, and the frequencies of omega and kappa, and make the orbit sort of close in the rotating frame. And this is what cleverly used by Lindblad, and it shows that that orbit can be closed in the rotating frame, and they sort of can be arranged in such a way, synchronized. Orbit can be synchronized in such a way they give an impression of a bar and spiral structures in the galaxy. Although there are, as I mentioned, about billions of stars in the galaxy, actually stars never collide with each other. Okay, this can be understood from the fact that the mean density of stars is extremely low, is about 1 in parsec cube, and this can be understood again from the next nearest neighbor, our stars in the Proxima Centauri, which is at a distance about 1.3 parsec from Sun. And the collision cross sections one can actually determine, and then the simple high school physics one can actually find the mean free path of a star, and it comes to extremely large. So mean free path of a galaxy are so large than the size of the galaxy that the stars rarely collide in galaxies compared to what we know the gas in our room, where the collisions of the mean free path are extremely small, so that the gas molecule would actually collide immediately as it starts to its journey. Let's look at the formation pictures of galaxies. So here I show a small cartoon sort of showing that how the snowballs grows. The snowballs initially starts with a very tiny foam, tiny spheres, and as it rolls and it accumulate more and more snows, and it grows over time to a big structure. Okay, this is sort of the bottom up scenario, and it seems the galaxies are also grow in the similar fashion. So small galaxies form first, and they sort of merge with the small satellite galaxies, and over time they grow bigger and bigger, and to make the what it looks like a present day galaxy. So in other words, the small galaxies form first, and they grow via merger, accretion, or star formation to grow a bigger galaxy what we see today. So a merger could be like sort of dry merger and wet merger. Dry merger means without gas, and wet merger with gas. However, in a real galaxy mergers, like their galaxy always have gas that we have just understood. So it's most of the time mergers are likely to be wet mergers. And in mergers, what happens is that the two galaxy merge with mass m1 and m2, and if there is no destruction of material or losing material, then the total mass would be m1 plus m2, and merger, whether it's dry or wet, it helps growing a galaxy stellar mass and brings fresh gas and stars, and also it helps mixing sort of stellar population in the galaxies. And this is sort of one can see the smaller galaxies form first, and one can actually these two galaxy will merge with another one to make it a bigger, and this is sort of one can grow what is called a merger tree of a galaxy. And that's the kind of the thing that we wish for to construct for every galaxies that we see in the universe. But we have to take it slow, and we have to establish that this is the process, and for which there are enough observational evidences. There are, apart from the mergers, the galaxy could be also accreting gas from surrounding medium, and accretion brings cold gas to the galaxy. And cold gas is the fuel to make new stars. When the gas comes to the galaxy, they may be compressed and lead to a burst of star formation. And this burst of star formation can actually make new stars, and sometimes, depending on the chemical enrichment of this accreting gas, there can be massive stars forming, and these massive stars would explode and spill the material all over, and it's sort of like the it's like a it's like a polluting the material or the gas which is existing in the galaxy through this star formation, and then the explosion of the massive stars through supernovae. And so this is like a feedback to the galaxy in a sense, and this has a profound role in shaping what galaxies are today, actually. Star formation. So stars form in the molecular cloud, and it seems that we can actually estimate the star formation rate in galaxies. So it's you calculate the amount of young stars that is forming. So one can look at the various tracer of the star formation. For example, very recent stars formation, one can look at the hydrogen H alpha or the Balmer series lines in a hydrogen atom, the emission lines. One can use the hydrogen alpha, hydrogen beta, or the metal lines, one can, or the far ultraviolet emissions. So there are many tracers of star formation in galaxies. So one can estimate the star formation rate, and this is being plotted on the y-axis, and then the x-axis is plotted the stellar mass of the host galaxy. And what we know from the SDSS, the Sloan Digital Sky Survey, that the star formation rate sort of follows the stellar mass. In some sense, there's a one-to-one correlation, and this is being also studied in many galaxies that are distant galaxies that are at higher and higher redshift, and these red dots are actually showing galaxies that are with redshift greater than 4.5 actually. And if you look at our on this plot, it seems like this is the Milky Way is falling somewhere around here because its stellar mass is somewhere between 10 to the power 10.5 or a bit more. And then it is making stars at about 1 solar mass per year. So this Milky Way is very close to the galaxy main sequence, and so are the many high redshift galaxies. The important point to note here that when the galaxies stop making stars, so the star formation rate would fall, then the galaxy would go below the main sequence. So that's something we must know. Milky Way is not yet. Then we can look at this, like the problem of the galaxy evolution, where we can see the galaxies in the local universe. They're very matured and they're big, massive, right? And if we look back into the early universe, so for example, a redshift 1 to 2, when the universe age was about 6 to 3 billion years old, the galaxies completely, they look different. They're clumpy, they're irregular, there are hardly any structures like that we see. And if we look at the galaxies even earlier, in fact, like now the very early universe, then they look even different. Of course, we have limitation due to the telescope resolution, but thanks to JWST and Hubble, that we can actually now look at galaxies in the first billion years. And these galaxies are typically low mass, and many of them are low mass, metal poor, and dominated by young stellar populations compared to their local counterpart, which is like massive and metal rich and dominated by old stellar populations. The study of galaxy evolution are basically connecting these two phases. So that's a very complex process that we must understand to understand how galaxies grow from this phase, early phase, to what we know today. One can sort of understand this from this small cartoon that I like, analogy rather, of a small village where to if it ever grows to a gigantic city, and it's a city like this. Now, of course, like this city did not grow just in one day, right? It expanded over many years, and it hosted like multi cultures, like a diverse population. So there have been a lot of inward migration to the city, and that all of them have resulted in a sort of like metro culture, or in a city which is completely different from a small town, where there is a small town where the populations are sort of uniform, and a little diversity, rather, compared to this. The similar thing might be also the case when you look at a small galaxy, a dot that is in the first billion years, and that you see today galaxies are like this. And from here to here, it's a really challenging process. And I explain again here through this is that if you see a tadpole and you see a toad, immediately one would say that this tadpole is like sort of will grow to a toad. And same analogy you see is like a small galaxy. We do not know whether this one will grow here. in the case of tadpole and toad, we know the full cycle of the fog. So we know actually that this is for sure. What we don't know is the full life cycle of a galaxy. And that's where it becomes challenging. This is one of the biggest challenge of galaxy formation and understanding evolution in astrophysics. Let's look at the observational evidences now. So Milky Way galaxy, you can see it's like in this map here. And these are the two LMC and SMC and the Magellanic Stream. And Milky Way is also currently sort of interacting with the Sagittarius satellite. So it's like Milky Way is not quite. Milky Way is currently interacting with LMC, SMC, and Sagittarius satellite. This is where one can see that the orbits of the satellites. There are many LMC, SMC, Sagittarius, Fornax, Leo 1. The orbits of 11 satellites that are currently interacting with the Milky Way are shown in these plots here. These are useful because we know when and how the path of these satellites were. Actually, we can do the backward integration and then find out like where the satellite came from actually. Probably. Milky Way just do not have only 11 of the satellites. It has about 60 satellites. Actually, most of them are pretty faint, so that we cannot actually see them. In summary, the Milky Way is not an isolated galaxy. It's actively interacting with other galaxies and satellites. And so are many galaxies in the local universe where they are interacting with a companion or another galaxy and a galaxy. So binary interactions are not so uncommon as well, as we see. But from the local universe, this study from the Sloan Digital Sky Survey through the GalaxyZoo project, it shows that the merger fraction, actually measure merger fraction. Measure merger means two galaxies with a similar mass, like M1 and M2, you remember? M1 and M2 are almost similar. So they are their major merger. So their fraction is like actually quite small, it's a few percent. And this is slightly at a higher redshift, and from redshift about 0.2 to 0.7. This studied the Hubble in the GEMS survey, and they studied about 400 massive galaxies, and only 7 are shown, 7 pairs are found. So again, this shows that the pair fractions are actually pretty small. Now this is also very difficult to detect, difficult to observe, because we know from the simulations that mergers are recognizable for only about 250 mega a year. If we wait longer enough, they will merge, so we wouldn't see them, right? So it's a very difficult window and timing that is required to actually detect them. So possibly that the galaxy might be merging more frequently, not just major merger, but smaller galaxies might be merging more frequently. Now, there are also studies that have tried to look for Milky Way-like system, and this is a very interesting study of satellites around galactic analogs, the Saga survey, which found 101 Milky Way-like system, and is in one of the Milky Way like galaxies have about 6 satellite galaxies that is going around. And this is a very, very interesting, try to tell you how Milky Way is it unique, or one can actually find out that whether our galaxy is unique through these studies. Now, it is not just the mergers are the only way to find the galaxy interactions. There are stellar streams which also sort of the fossil signature of galaxy interactions. And in this case, the studies on the Andromeda are quite fascinating and quite and advanced our understanding of how stellar streams can be used to understand the history of this Andromeda evolution. And sort of this is where you can see the inner part of the Andromeda, and this is basically the halo of the Andromeda. You can see this like linear like structures. These are the stellar streams. These stellar streams probably originate from when a satellite or the dwarf galaxy that fell into the Andromeda and the halo, and they sort of got disrupted or like shredded by the galactic potential, and they sort of appear like a streams of like stars. These are streams of old stars, and mostly the RGB stars, like through which we can actually find out this locate these streams. Now there are basically evidence of two ancient migrant events, and when this globular dwarf galaxies, of the satellites, sorry, when they fail and then they form these streams, they also not only brought the stars which got mixed in the halo, but they also got globular clusters with them. These globular clusters, these are the star clusters, and they sometimes are associated with the streams, and sometimes some are not associated with the streams. So they can also be used to basically separate the origin of the streams in stellar streams in the Andromeda. Stellar streams are also found in dwarf galaxies. So you can see like in dwarf galaxies, smaller dwarf galaxies, and stellar streams with the deep photometry are now seems to be common in actually like galaxies. You look at the galaxy, which is like an SDSS galaxy new, with the deep photometry, you can see like the amazing structures around these galaxies. The streams are basically formed by old stars that we see in the deep imaging, and they are the fossil record of a galaxy's past interaction with satellites or companion galaxy. In other words, stellar streams lay the foundation to study galactic archaeology. And thanks to the Gaia satellite, and this is the streams, stellar streams are around the Milky Way. It seems there is a swarm of stellar streams, or the satellite galaxies, or the dwarf galaxies that fell into the Milky Way, and there are about 41 stellar streams found in the recent study in the Gaia using the Gaia satellite. The stellar streams kind of present you a jigsaw puzzle that you have to stitch them together to reconstruct the evolutionary history of our galaxy. It's like a as a detective. You have a small pieces of information gathered together to create a bigger story about the history of this galaxy, the way it is. Not just the streams and the mergers and this, but when the galaxies in the high redshift also gives you an understanding of how we can understand the galaxy evolution, and in this context the Hubble's contribution has been extraordinary, because the Hubble, when looked at the very fairly empty patch of the sky in the southern hemisphere near the Fornax constellation, and it just found that there are hundreds of thousands of galaxies in this space, and most of them are distant galaxies. So Hubble sort of opened a new window to look into our past. Actually, the past, the past of our universe. So how you do this? So now, of course, it's like the JWST era, and then JWST has created a even more stunning image, and one can actually push the boundary where Hubble sort of studied so far, actually, right? And then the JWST is basically taking the frontier of the galaxy formation to almost at the beginning of the universe, and one can study this the properties of galaxies in terms of a redshift slices. Okay, this is very much possible. We can make a fairly large map of galaxies in the local universe. There is a thanks to a huge number of the telescopes dedicated for doing this. For example, the LSST is one, SDSS, DAISY. There are many such telescopes which are actually dedicated to study the local universe, galaxy in local universe, and we can use the similar surveys from different telescopes and to make a redshift slice and to study the properties of the galaxies as on an average sense, in a statistical sense. And thanks to this JWST again, and then we can actually now look at the galaxies in the first billion years. So the sort of the first generation galaxies, we could say. And this is an example of a redshift 10 galaxy when the universe was just 400 million years after the Big Bang. Although JWST works in the infrared bands, because of the redshift, the light will be like actually like emitted in the UV, so rest-frame UV. So JWST more or less like looking at galaxy properties in the rest-frame UV. And this is one of the surface brightness plot of a galaxy, and this is the data that we measure from this galaxy, and from there we can sort of model this galaxy and construct what is the surface mass density of galaxies. It seems is about 10.3, which is quite high compared to the Milky Way, like stellar mass density at the center. Not just the density of the stars, we can compare now from the local to the high redshift. We can also compare how the galaxies are chemically different between today and to the galaxies that are the farther away or in the past. So this is one of the study showing that the metallicity, which is measured in terms of oxygen abundance in the galaxy. So it's like O over H means it's the oxygen abundance versus the stellar mass on the x-axis, and one can see that a redshift 7 to 10 galaxies are basically very, very metal poor compared to the redshift 0 galaxy, where more or less they are sort of the solar metallicity depending on their stellar mass, for example. Sorry. And this is where the Milky Way is actually falling on the this mass metallicity relation. JWST now, of course, allowing you to, like, as I said, like, the pushing the frontier of the galaxy formation to almost at the very beginning of the universe and close to the dark age, the cosmic dark age, where we do not expect galaxies to be seen. But JWST is actually like, sort of going almost close to that, and it's quite an exciting time to study galaxy formation and evolution. In this sort of simulation movies, one can see the whole galaxy formation that we just described, actually. So it's a beautiful movie from the Illustrious TNG team showing how galaxies actually accrete gas, and they sort of like grow over time and form a spiral structures that you see, and as early as like starting from about billion years after the Big Bang. Okay, and one can actually also understand in a larger context how the gas streams are fed to these galaxies, actually. This is an edge-on view. You can see a very beautiful spiral structures forming almost when the universe was just 4.2 billion years old. It's also trying to show you the galaxy's stellar mass, how it's growing. Because this gas, when comes in, so they make stars, so the stellar mass grow, and also it brings like new objects like the satellites. It's quite fascinating. Thank you for your attention.